Welcome. Low frequency response of EMOSFET. Topics which I'll cover under this section is current relation in common source amplifier, low frequency model, actual common source amplifier, AC analysis of common source amplifier, and video presentation on similar lineup of this presentation. So small signal model. Here this is an symbolic representation of EMOSFET. So we can see that or we have seen in the previous sessions that the drain current, previous session in DC analysis of EMOSFET, that the drain current is a function of gate to source voltage and a drain to source voltage. So if at all there is some change in the drain current, say by little proportion or little few amperes or milliamperes, then ID plus delta ID, this will be written as a change in the two parameters, that is VGS and VDS. So it's a function of VGS plus delta VGS and VDS plus delta VDS. So we will expand it by using a Taylor's theorem over here. So ID plus delta ID is equal to a function of delta VGS comma delta VDS plus the differential change in the current with respect to the parameters of VGS and VDS. And since it's a very small change, we can say that delta VGS is equal to VGS and delta VDS is equal to VDS. Now here delta ID is a function of VGS and VDS, and these respective changes, this can be written as ID is equal to delta ID upon delta VGS when VDS is kept unchanged, and delta ID upon delta VDS when input gate to source voltage is left unchanged. So this will give you a value of transconductance, and this particular factor will give you a value of drain resistance, so which is equal to RD, or it is inversely proportional to drain transconductance. So writing this equation over here, ID is equal to GM VGS plus 1 upon RD into VDS. So small signal model, here I have drawn the small signal model of this based on this equation. So ID is an input current, voltage across it is VGS, and GM VGS is the current, and VDS upon RD. So that is also one portion of an current flowing through RD. So here resistance is drawn RD, and output voltage measured across it is VDS. So this whole combination is a small signal model of EMOSFET, enhanced metal oxide field effect transistor, and this will be using for our analysis. Hope this will make you clear. So now we have drawn this low frequency model. Fine. Now we are going to see that if there are slight changes due to VDS, then what will be its impact? So drain current is mu times C0S W by L. C0S is the capacitance, internal capacitance at the junction. So mu into C0S W by L, VGS minus VTH whole square upon 2 into 1 minus lambda into VGS. So if VDS, that is drain to gate sources, source voltage is greater than gate to source voltage minus the threshold value, which is defined as a pinch of voltage. So transconductance GM, that will be taking a differential value of the drain current with reference to your gate to source voltage. So it will come out, differentiate this above relation ID. So mu times C0x W by L into 1 plus lambda VDS into VGS minus VTH. So the drain resistance is 1 upon delta ID upon delta VDS is equal to 1 upon lambda into delta ID. So here what it shows that this is the level of VGS, which is a AC signal. Now that VGS is proportional to change in both the direction, go negative as well as positive. So this change in voltage will lead to another current change, which is shown over here. So a complete model. Now it has a resistance RD. Fine, this is your field effect transistor and this is the variable voltage VGS, as well as your signal voltage. So based on that, this model has been developed. So conclusion is that you have seen the variation of current. You have seen that current is a function of VGS and VDS, and by the variations in these voltages you have come to a conclusion that current is a function of changes in VGS and VDS, as well as the changes in the current due to the gate to source voltage and drain to source voltage. And we have defined these changes in terms of transconductance and drain resistance, and we have modeled this CS amplifier. So just a conclusion. Now this is an characteristics input this is an output characteristic. Fine, ID versus this is an input characteristic which shows that variation of drain current with reference to the input voltage. So whatever is the slope measured over here, it is GM, and this is a Q point. So your VGS is varying in the negative direction as well as in the positive direction. So for DC analysis, the DC voltage is short circuited and capacitors are open circuited, and for this model, this being short circuited and this is capacitance, whatever are present, those will be short circuited, are open circuited. So based on this we are drawing the model. So here VGS, GM VGS and RD is the internal resistance, which is given by 1 upon GD, and RD is the resistance observed over drain terminal. So in this way we completed our frequency analysis and we have drawn the model for it. So let us see a common source small signal, a common source amplifier small signal analysis circuit. So here you can see the complete circuit drawn over here, and this is an AC equivalent circuit wherein wherein the DC voltages are short circuited and all the capacitances are open circuited. I will be seeing the effect of this RC combination at the input, how it will behave. Okay, AC equivalent circuit. So I have drawn over here. Go on the similar lineup of analysis what we have done for a bipolar junction transistor. So find out the input impedance Zi, that should be equal to R1 parallel R2. Output impedance from looking back into the circuit is RD, capital RD parallel small rd. If Vi is equal to 0, Vgs is equal to 0, therefore the current source GM Vgs is open circuit and output impedance is equal to Z0 is equal to capital RD. Then calculating the voltage gain. Voltage gain is the ratio of output voltage to input voltage. So putting this literature into an equation. So AV is equal to V0 upon Vi. V0 at the output stage is equal to I0 into RD parallel capital RD, which is equal to ID into RD parallel RD. So drain current is equal to GM VGS. So AV is equal to V0 upon Vi, which goes to give you minus GM RD. So this presentation of mine is followed by a small video which explains the low frequency analysis of EMOSFET, building the low frequency model on the similar lineup of my presentation.
Hi guys, in this video I'm going to show you what is a small signal model of a MOSFET. We'll derive it and figure out what is this circuit model of a MOSFET is equivalent to in terms of small signal model. So to start with, let's say the drain current that is flowing into the drain is a function of the voltage that is applied between gate to source. Let me put this here, VGS, and it's a function of VDS, which is the potential between drain to source. Now in order to find small signal model, let's say if we actually change VGS by a delta VGS and VDS by a delta VDS, there would be a change in ID. Let's say that is delta ID. So let me write that. In which case, if we assume that delta VGS and delta VDS are small, that's the point of talking about small signal model. If you assume these two are small, then the resultant delta ID is also assumed to be small. So in that case, we can expand this function by using Taylor series expansion only till first order. Because as these values are small, this function can be represented with just the first derivatives itself, no need of second and higher order derivatives. We'll go into details of that after completing the MOSFET small signal model, and in fact in general the philosophy of small signal model. So if we expand that, we can write ID plus delta ID is equal to f of VGS VDS plus partial differentiation of ID with respect to VGS times delta VGS plus partial differentiation of ID with respect to VDS times delta VDS. Now the key here is the assumptions that we made. Delta VGS is small. We are taking it to be small VGS, and similarly delta VDS we are taking it as small VDS, and similarly delta ID as small id. Now if we rewrite this expression, it would be this value, in which we can say that f of VGS VDS is nothing but the capital ID. Hence we are going to say this value and this value are in fact equal. In that case we can say this value, that is small id, is equal to this value. So now our interest is only pertaining to the small id value, which is because of a small change in VGS and VDS, which is resultant, that is id. Now let me write only this expression. In fact, a very important point to note here is this value is for a given VDS and this value for a given VGS. We are going to define two terms. One is this partial differentiation at a given VDS. We are going to call this GM, the transconductance, and this term, which is GD, this is drain conductance. In fact, in most of the cases we write GD is equal to 1 over RD, where RD is the drain resistance. This entire equation can be written equal to this equation. Now the drain current that is flowing can be equated to this value with respect to the input voltage VGS, in fact input small signal voltage VGS, and the drain to source small signal voltage VDS. Now let's represent this in circuit diagram, which would be, let's say we take this as a drain terminal, and the current that is flowing into drain is ID, which is what we have derived here. This should be equal to, one is GM times VGS, so it depends on voltage between gate to source. Hence we have to take the gate terminal. I am taking gate terminal here and source terminal here. And of course what happens to gate to source terminal side is there is an open circuit here. Because of the oxide, there wouldn't be current flowing through gate, hence this is always open. I am taking this open and calling this VGS. If you know the voltage applied across the gate to source is VGS, that is the small signal gate to source voltage, then the current that is flowing can be represented as a voltage dependent current source, because this is the first term we are representing here, that is voltage dependent current source, and that current flows from drain to source. Value is GM times VGS, and ID is equal to GM times VGS plus there is second term which depends on the voltage across the drain to source. So this is source terminal, this entire thing is source terminal, which is common. So the potential between drain to source is VDS. Now if you take this drain resistance in parallel to this, so that the entire ID is divided into two segments, one is GM times VGS and the second one is the current resulting because of the voltage drop across the drain resistance, that is RD. So the current that flows through this RD is nothing but VDS over RD. That's what is written here. This is the second term. This is a low frequency small signal model of a MOSFET. Now as we know the drain current equation, which is given by mu Cox prime W by L times VGS minus VTH whole square by 2 times 1 plus lambda VDS. We have taken this equation in saturation because we use the MOSFET especially in saturation region for analog applications where we need this small signal model. Of course, we have to make a point to verify that we are operating in the saturation region when we are doing the analysis. That is, VDS is greater than VGS minus VTH. Now we can find the value of GM from this equation, Gm is the differentiation of this ID with respect to VGS, which is equal to mu Cox prime W by L times 1 plus lambda VDS times, if we differentiate this, we get 2 here, 2 gets cancelled, we get VGS minus VTH. So this would be the transconductance of the MOSFET. And if we get to the drain resistance, in fact, drain resistance is 1 over del ID over del VDS. So we can write this. If we find this value, del ID over del VDS from here, when we differentiate, this entire term doesn't depend on VDS, hence this will be constant after differentiation. It will come out. If you look at this term, this one differentiation is 0 plus differentiation of this would give us only lambda. So in fact, this entire term times lambda would be present when we do del ID over del VDS. So which can be written as lambda times ID approximately. We can write this as 1 over lambda times ID. If we observe this equation, which is drain resistance, depends on the channel length modulation parameter lambda. If there is no channel length modulation, lambda would be 0. In that case, 1 over 0 would be infinity. The drain resistance, if we assume channel length modulation is not there, would be infinity, which means this RD, when it is infinity, this 2 points would be open. This entire segment is open. If you assume channel length modulation, there would be RD term present here, a parallel resistance. When we see this circuit symbol in a circuit, if you want to do small signal analysis, we have to replace this circuit symbol with this equivalent small signal model. Now let's see the philosophy behind the small signal model. Let's start from this equation because it contains both the DC current because of the DC voltage is applied and small signal current because of the small signal voltage is applied. Now if you look at this, the assumption with which we started was that, let's say there is VGS, which is with respect to time, VGS is constant, capital VGS, and we are assuming there is a delta VGS that we are changing on top of it. Let's say that delta is around this value. Let's say this is delta VGS. We said this change is very small, so that we equated this to a small signal VGS. So let's say this might be a small sinusoid that is riding on top of this big DC VGS value. Now in that case, when we did the Taylor series expansion, we got that the DC current was equated to a function which is dependent only on the DC values. So the DC was completely not dependent on the small signal values here. But when you see the small signal that resulted because of the changes in the voltages here, that was depending only on the small signal values, small VGS and small VDS. But of course, there were parameters like delta ID over delta VGS and delta ID over delta VDS. These are the two key parameters which we defined them as Gm and 1 over RD. If you look at this, Gm is a small signal parameter value and RD is a small signal parameter value represented in this small signal model. But if you observe carefully, if you look at the definition, this differentiation was done at a given VDS, which means at a given DC voltage, this partial differentiation was taken, which means the small signal model depends on the DC biasing point. Now let's come to the DC biasing point. So let me take an example circuit here, that is, let's say RD, and we have a MOSFET here. Let's say the voltage that we are applying at the input is a small signal, plus there is a VGS that we are applying, which is DC. Because of this DC potential supplied across, there is a DC current that is flowing, capital ID. And because of this small change in this VGS, there would be a small change in ID. That's what we are talking about. because of which even the VDS that we are saying here would have a small change, VGS. Now we have seen if these changes are small, according to Taylor series expansion, this can be accurately represented with a linear model, which means however the characteristics of a circuit is, even the circuit is non-linear, if the signal applied is small, at that given point of operation, that is the DC biasing point, we can take the circuit to be linear. For example, let's say the earth is close to a sphere, but still when you stand across and see, you see flat surfaces, which means the region we are seeing is very small compared to the entire sphere. Hence it looks flat. So the same way, if you look even the characteristics of MOSFET, that is, I have drawn this graph very roughly, don't take it literally. Let's say a VGS, capital VGS is here, and around this point, of course this entire curve is non-linear, but around this, if the delta is very small, let's say this delta is going to be only within this range, this can be approximated with a line of some certain slope which we have GM, the slope. So this is what we say, around a given DC biasing point within a small signal value, the nonlinear characteristics can be taken as linear. When they are linear, when we observe this, the DC biasing is completely independent of this AC model. But of course, the AC model is not completely independent of the DC because there are parameters which are derived from the DC biasing point. But this equation tells us that we can do DC biasing separately and get the AC parameter model values and do AC analysis separately, so that we are not interdepending on each other. So what does that mean? That is, let's say we have the circuit here. So when we are doing AC analysis, we represented that ID is equal to this value. We didn't even take into consideration the DC parameters. But of course, the GM and RD depend on DC biasing point. That we should never forget. So when we are doing small signal analysis for this circuit, let's say, the DC biasing parameters should not be considered while doing small signal analysis. So we completely neglect this so that we do only the AC parameter analysis. In that case, the first point is all the DC voltage sources should be shorted and DC current sources should be opened. Because we are assuming these voltages are zero, the effect because of this DC biasing should not be considered during AC analysis. Hence, we are taking DC voltages are zero, hence short circuited, and DC current sources are zero, which means open. When current source current is zero, it is open. And then we will do the analysis of small signal. So let me represent the equivalent circuit of this one. That would be small signal. It's coming here. This is gate terminal, and we have source grounded here. Source is grounded, and we have drain terminal here. Drain. We know the equivalent circuit between gate, drain, and source that we have seen here. So let me put that across. That is like this. Now if you look at this, this drain to VDD is RD. Now this VDD is anyway shorted, which means to ground. VDD is 0, ground for AC analysis. Then we would get even this RD here. And of course, this terminal is nothing but the V out. So this is the V out for us. So this is V out. Now here this is VGS. This is nothing but the source that is applied here. Now we can find what is the current here. This is GM times VGS, and we have everything. Now of course in this video we are not going to find what is amplification and so on. This is just to show you that DC biasing and small signal model. So when we are doing AC analysis or small signal model, the DC dependent terms are made zero because we assume that the circuit is linear around the DC biasing point, so that we can actually take the DC biasing separately, AC analysis separately, and add them because the circuit is linear.